Hello everyone, welcome back to Math 1351, more on math. Today we're going to talk about Chapter 11, Section 2. You notice I'm now going to try to type out my stuff because my handwriting is horrible. So, let's look at the objectives of Chapter 11, Section 2. We're talking about definitions of common terms. Common terms. Okay, my objectives. We're going to discuss simple, closed, and complex curves, including polygons. Remember, polygons, poly means a lot, many. Gons are talking about angles and sides. So we're talking about items or objects that have many sides. We're going to talk about naming and classifying triangles and quadrilaterals. We know that triangles have 3 angles, or 3 sides also. Quadrilaterals. Quad means 4. Laterals are lines. So we're going to have with 4 lines, like a square or a rectangle. We're going to look at the hierarchy among selected polygons. There's an order in which they are designed and developed. Then lastly, we're going to talk about symmetries and the relations to planar figures. When we say about planar, it's on how they relate to a plane surface. Alright, so whenever you hear the word planar, that's what it means. So, if we took a pen and drew a path on a piece of paper without lifting the pencil, and without retracing any part of the path, so in other words, if we start somewhere and keep on going, then a couple things happen. The drawing is restricted to the piece of paper. True, I can't go outside the paper, I can't go above the paper. By not lifting the pencil implies that there are no breaks in the drawing. True, I mean, if it's that's a definition of continuity. It's continuous. Once I start to once I stop, that's a continuous drawing. Then, if those two conditions are applied, then we know the drawing is connected and it's a curve. Okay, in geometry we talk about curves. Anything, it could be a straight line, it could be a curve, it could be a bend, almost a complete circle. So we're talking about connected and curves. Let's look at the common terms we're going to be using. We're talking about simple. We're talking about a curve that does not intersect itself. A simple curve. A curve that does not intersect itself, except maybe at the starting and stopping points. In other words, for example, a circle, or any other thing we just defined. As long as it continues without lifting the pen or pencil, and it doesn't overlap itself. That's a simple curve. A closed curve. A closed curve is a curve that can be drawn by starting and stopping at the same point, like a circle, or an oval, or a triangle. Polygon. A simple closed curve with only segments as sides and vertices as junctions of the sides. Ooh, that's interesting. It's a simple, meaning there's no intersection, and it's closed, meaning it starts and stops at the same place. So, like I said, a triangle or a square or an oval. But the problem is, now it says conditions with only segments as its sides. This is oval is not made up of segments. A segment is a straight line that has a beginning and an end point. Vertices are the points where 2 lines intersect. So if I have a segment there, that's a vertex. So the vertices are the junctions. So a polygon has straight sides, straight edges, and a vertex between the 2 corresponding sides. A vertex is a point where 2 sides of a polygon meet. Here's one side, here's another side. Where they meet is a vertex. Now we have convex versus concave. Convex. A simple enclosed curve that has the properties that the segment connecting any 2 points in the interior of the curve, interior means inside of the curve, is wholly contained in the interior of the curve. That means any points we pick has any segment, so any line we draw is going to be inside that picture. Or a polygon with every diagonal connecting 2 non-adjacent vertices entirely in the interior. Remember, here are our vertices. Let's call this A, B, C, D, E. A polygon with every diagonal. A diagonal is from A. That's not a diagonal because that's a common side. That's a segment. So a diagonal is it's connecting 2 non-adjacent vertices. A and C are non-adjacent. A and B are adjacent. A and E are adjacent. E and B are C and B and C and D are adjacent. They're next to. Adjacent means next to. So these are two vertices that are non-adjacent entirely in the interior. So between A and C, between A and D, those are diagonals. Between B and E, B and D, between C and E, and C and A. So that's what we're saying. And it sounds like a pentagram. It does help. I'm sorry, but that's what it's saying. That's how we know it's a convex. If every line segment or every diagonal we can connect from the non-adjacent points, or every line segment is inside the polygon. A concave polygon is a simple closed non-convex curve. It's non-convex, meaning, in other words, what it says is I can't draw the any segments and it still stays inside there. It is possible for a line segment connecting 2 interior points to contain a point or points outside the interior of the curve. So let's look at, we have A here, B, C, D, E. Those are vertices. If I go from A to C, all these points are outside the curve. That's what concave means. All right, let's look at, see if we apply these to just other curves. Okay, this is a curve. Is it simple? No, it starts and stops. Is it closed? No. Is it a polygon? No. Since it's not a polygon, it can't be convex or concave. A polygon has to be made up of line segments and has to be closed. So that's all that was. How about this object? Is it simple? Yes. Is it closed? No. Beginning and end points are not the same. Is it a polygon? No, because it's not closed, it can't be a polygon, therefore it can't have convex or concave. Is this a simple curve? Does it overlap? Nope. Does it begin? Yes. Does it end? Yeah. Is it closed? Yes. Is it a polygon? No, because it's not made up of line segments, it's made up of bendy lines. So it's not a polygon. Is it convex or concave? It has to be one or the other. So if I can pick any 2 points, and any point is outside the polygon or the curve, then it's concave. It's not convex. See, that's convex and concave. So, all right, a circle. Is it simple? Yes, it begins and ends. Is it closed? Yes, it begins and ends. Is it a polygon? No, because it's made up of bendy lines instead of line segments. Is it convex or concave? Well, any point I pick inside here is made up of interior line segments, so it's convex. This figure. Is it simple? No, because it crosses over itself. It intersects itself, so it's not simple. Is it closed? Yeah. There's no opening anywhere. Is it a polygon? Now remember, a polygon has to be simple and closed. It's not simple, so it can't be a polygon. Is it convex, concave? Well, since it's not a polygon, it can't be it can't be any of those. How about this object? Is it simple? Yes. Is it closed? Yes. No openings. Is it a polygon? Yeah, made up of line segments. It's simple and it's closed, so it's a polygon. Is it convex or concave? In other words, I can't draw any 2 points. I can't draw a line between any 2 points, and it's not inside the curve, so it's convex. Remember, convex is every line segment is inside that curve. How about this? Is it simple? Yes. Is it closed? Yes. Is it a polygon? Yes. It's made up of line segments. Is it convex or concave? Well, since I can go from this vertex to this vertex and it's not inside, it's concave. This windshield wiper thing. Is it simple? Yes. Is it closed? Yes. There's no opening. Is it a polynomial? No, because it's got a curve. Is it convex or concave? Well, can I draw any points that are not contained within it? No, so it's convex. Alright, so that's what we look at whenever we do these kind of things, is you have to see how it fits the definitions. So every simple closed convex curve separates a plane. So if I have a plane, here's plane alpha. Every simple closed curve separates a plane into three different subsets. Here's the curve. It has exterior to the curve. That's the rest of the plane. Interior of the curve. That's the inside there, the gold part, yellow part. And the curve itself, the frame. Those are the three distinct parts that any simple closed curve creates on a plane. Now, the outline and the interior of this polygon is called the Polygon Region. So when we talk about the Polygon Region, we're only talking about the outline and the interior of that shape. More about polygons. Polygons are classified according to the number of sides or vertices they have. So let's look at this. It goes by the name. Triangle. How many sides does it have? Tri means 3, so it has 3. It has 3 sides or 3 vertices, 3 points. Quadrilateral. Quad means 4, so it's 4. Pentagon has 5 sides. Hexagon has 6. Heptagon, hept is 7 in Greek. Yes, in Greek. Octa means 8. Nona means 9. Decagon, deca means 10. Hendecagon means 11. Dodecagon is 12. And you go on from there. I mean, go Google the rest of those names. But it goes into what we call n-gon. It has n sides. So if it has 47 gon, we put 47. So yeah, in the real world we use the numbers. So if something has 73 sides, we call it a 73 gon. It has 73 sides. Alright, so let's look at this. So when you have a polynomial, a polygon, you have the vertices A, B, C, and D. you have the internal angles. It's alpha, beta, gamma, delta. Whenever you hear consecutive vertices, these are two vertices of a polygon connected by sides. So here's a side. A and B are connected by a side. B and C are connected by a side. C and D are D and A. Those are all consecutive vertices. Consecutive angles. Two angles that share a side. So this angle alpha, angle beta, share that side there. So angle beta, angle gamma share this side here between B and C. So consecutive angles share a side. Consecutive vertices share a side. Consecutive sides. So here, this side and this side, they share an angle. So you notice the angle has both ends touching a side. So two sides are consecutive if they share an angle. This is how we name and define geometric figures. Naming polygons. Let's look at this. Refer to by capital letters the consecutive vertices A, B, C, D. So the angles, the vertices are always in capital letters. The angles are in Greek letters, and the sides are usually labeled by lowercase letters. So let's call this side A, side B, side C, and side D. Now, when we name these things, you notice that A, B, C, D, we can go C, D, A, B, or B, C. Then when you name them, you pick a point and then you go clockwise direction. So that's the way you read it, left to right. We're used to reading clockwise. Now, an interior angle. Interior angles are any two sides of a convex polygon having a common vertex. It's interior. So that's the angle of the polygon beta is that one. All right, so that's an interior angle. Exterior angle is determined by a side of the polygon and the extension of the continuous side of the polygon. So here's a side of a polygon and you keep it extended. That is an exterior angle. This is number 2. This is number 1. Actually, all of these are number 1. And a diagonal. Any line segment connecting non-consecutive vertices. So a diagonal from A would only be to C. From vertex A to vertex C. From B, the only diagonal you can make, it's it's non-consecutive. Those are called diagonals. And there's a whole bunch of words we're using here. Congruent figures. When you read the word congruent, we're going to use that symbol there. An equal sign with a tilde over it. That means it's congruent. It means more than equals because it has the same size and shape. It's a perfect copy, a duplicate of each other. Congruent segments have the same measure, and it's written, remember, segments, the segment here is AB, that's between AB, or BC, or CD, or DA. If you're looking at two segments and they're exactly the same, then we write them the segment names with that congruent symbol. Congruent angles. If two or more angles have the same measure, then we write the angle ABC is congruent to angle DEF. That means they have the same angles, the same side lengths, everything. All the measures are the same. Or we could get here, the measure. These are the angles themselves. The measure of angle ABC is congruent to the measure of angle DEF. Then we know that triangle ABC is exactly the same as triangle DEF. Now, note, you can't write them as line segment AB is equal to line segment DE, because this symbol here means that they're equal. Everything about them is equal. Well, they can't be equal because they have different points. So that you cannot put. What you could do is, if you're going to do equals, then we're going to have that. But congruent means the same length, the same angles. Equals means everything is identical. The same point, the same locations on the graph, everything. You could also, if that's true, and this is true, what this says is the line segment AB is congruent to line segment DE, meaning everything about it's the same. It's the same length, same angle from wherever else it is, so it's a copy of it. Whenever you hear the word regular polygon, a regular polygon simply means are polygons that are equal angular and equilateral. In other words, equal angular simply means they have the same interior angles. All interior angles are congruent. They're all the same, equal angular. Equilateral, all sides are congruent. That means all the sides are equal length. Here's some examples of them. A regular triangle, we call that, since remember, all angles and all sides have to be the same, that's an equilateral triangle. The length of these sides are all the same. That's how you write, signify that they're the same length, the same sides. When we do the angles, that tells you that all the angles are the same. If we had, let's say, an isosceles triangle, where these two are the same and that one's different, these two angles are the same, that one's different. Regular quadrilateral square, all four sides are the same and all four angles are the same. We can either put the angle symbol, or since they're 90-degree angles, we could put that triangle. Regular pentagon, all five sides are the same length, all five angles at the vertices are the same angle. Again, regular hexagon, all six sides are the same, all six angles at the vertices are the same. So that's, whenever you hear the word regular, that means that all the sides and all the angles are equal. Triangles and quadrilaterals. Polygons are classified according to their angle measures and side lengths. A triangle containing one right angle is called a right angle. There's a 90-degree angle. A case in point there is a flower, a tree, or a post. It creates a right angle to the ground. We also call that perpendicular. A triangle in which the angles are acute is an acute angle. Okay, acute means between 0 and 90 degrees. So all these angles are smaller than 90 degrees, like a yield sign. Obtuse. A triangle containing one obtuse angle is an obtuse angle. Okay, you cannot have more than one obtuse angle in a triangle. And we'll get to that in a little bit, but remember, obtuse angles are between 90 degrees and 180. Like, for example, the tail fin, it's called the rudder of an airplane. So you have one angle that's much bigger than 90 degrees because it's the swept back. A triangle with no congruent sides is a scaling triangle. No congruent, no equal sides. Notice that these are all different. An example of that is a jib on a sailboat. That's that front. It helps it steer or catch the wind when it's coming from a weird angle. A triangle with at least two congruent sides is an isosceles triangle. So if it has at least two sides, then it's isosceles. For example, it's the entrance of a Roman building, or anything follows the Roman architecture. You have those two sides are the same, and the base is much longer. A triangle with three congruent sides is an equilateral. All three sides are the same, like a basic tent. A trapezoid is a quadrilateral, something that has four sides, with at least one pair of parallel lines. So the top and the bottom are parallel, and the other two sides form some angles. The small window in front used to be in the corner of cars. If you remember, in the old days, you had the car, and always had this one small window here in the front. Because before the air conditioning was popular, that's this little window. When you're driving, you used to force air inside the car, cool you down. Alright, let's look at some more. A kite is a quadrilateral, four-sided figure with two adjacent sides congruent, and the other two sides are also congruent. You have two sides are the same, and the other two sides are the same. So you have two pair of congruent sides. Those two sides are the same, those two sides are. And it's the reason they call it a kite, because that's what the old kites used to look like. An isosceles trapezoid is a trapezoid with congruent base angles. Congruent means the same, base angles. So a trapezoid, top and bottom are parallel, and this means that these two angles are exactly the same. For example, a sine. Parallelogram is a quadrilateral in which each pair of opposite sides are parallel. A parallelogram. And it's four sides, so yeah, the top and bottom are parallel, and the two sides are parallel. And it doesn't have to, all four of them have to be, and it have to be the same angle. So the opposite angles are going to be the same. For example, the banisters, the shape of the banisters on a stairwell. If you're teaching, when you teach this thing, have the kids look at a basic stairwell. Because here you have a parallelogram. You also have a triangle, the base of the stairs. And if you look at the stairs themselves, you have rectangles. And if you look at the side of it, you have each stair is a perfect square. A rectangle is a parallelogram with a right angle. A rectangle is a parallelogram. Parallelogram, remember, has two pair of parallel sides. So the top and bottom are parallel, sides are parallel. And if one angle is a right angle, you always have to have the opposite side. Since those two are 90 degrees, the remaining angles have to be 90 degrees as well. So it has 4 90-degree angles. And it's just a little bit bigger than a square. A square has all 4 sides the same length, so those lengths are not the same size. If all 4 sides are the same, then it's a square, and all 4 angles are also the same. A rhombus is basically called a diamond. A parallelogram with 2 adjacent sides congruent. So this side and the adjacent side, that's congruent. And adjacent side, that's congruent. Adjacent to this one is that one. So rhombus is when you have all 4 sides same length, but it's not a square. It's shifted. You have 2 acute and 2 obtuse angles. Let's look at the hierarchy, the development, the rating, the ranking of how do they relate to each other. In the world of polygons, we're going to talk about triangles and quadrilaterals. There are many more, but we're going to limit ourselves to just these 2. Inside triangles, you have scalene and isosceles. Isosceles can also be equilateral. Remember, isosceles is you have 2 sides are the same and the third side not. But if the third side is the same, then it's an equilateral. That's why it's a subset. Equilaterals are subsets of isosceles. Isosceles are subsets of triangles. Triangles are subsets of polynomials. Or polygons, I'm sorry. Same with quadrilaterals. You have kites, trapezoids. And if you bend that kite, then you get to go. So, and you see how this thing works. This is how they're all related to each other. No, triangles are a proper subset of polygons. Yeah, it's a proper subset. Equilateral triangles are proper subsets of isosceles triangles. Because this one triangle can fit into this one. Isosceles, it could be equilateral, or it could be an isosceles triangle. So symmetry. Symmetry and its relations to planar figures. Planar, AR, figures. Meaning it has to do with planes. When teaching this to your class, use folding papers to introduce the concepts of symmetry. Because when you take a piece of paper and fold it in half, the line is going to represent the line of symmetry. And each side is identically the same, so it's symmetric. A geometric figure has a line of symmetry if both sides of a fold are identical. So if you take a circle and fold it haphazardly, then it's not the line of symmetry. But if you make it a perfect half circle on both sides are identical, then you have the line of symmetry. Examples of lines of symmetry. Okay, how many lines of symmetry do the following objects have? So if we could fold this one, we can fold it up and down. If we fold it back and forth, then this side is the same. We can also fold it this way, because this bottom side matches that side. we can fold it this way. That's 3 so far. How about if we do it, use diagonals? This side looks like that. That's good. This side looks like that. That's it. So we have 6 lines of symmetry. In this one, if we fold it in the middle, no, because the bottom part wants that. So this one, if you just take it through the center, then they're equal. So it only has 1. But this oval thingy, you cut it down the middle, both sides are the same. You cut it through the middle, the bottom is at the top. What if you did it to that way? And you folded it that, nope, that's not going to work. So it only has 2. Can you fold this anyways? If you fold it this way, will it work? No, because it's different. If you fold it across this way, this line will not meet with that one. You're not going to have any lines of symmetry. Alright, let's look at this. Rotational or turn symmetries. Because we just looked at lines of symmetry, straight lines that divide an object into 2 parts, 2 equal parts. Rotational does the same thing. Do we get equal representation of the shape itself as we rotate it? There's no folding in this one, it's just rotating. An object has rotational symmetry if the figure can be rotated between 0 and 360 degrees about some center point that it matches the original figure. No, remember the direction of the curve. If you go counterclockwise, that's a positive rotation. If you go counterclockwise, it's positive. If we go clockwise, it's a negative rotation. So, with this one, this is an equilateral triangle. This is equilateral triangle. So, if we rotate this, will they look the same? Yeah, because all 3 sides are the same length. And if we did it again, and we did it again. So, this one has has 2 rotational symmetries, because if you go, every object will have a rotational symmetry of 360 degrees. So if I took any object and rotated it 360 degrees, it's going to end up the way it looked. Duh, so we don't use that. So what is this one? Since remember, a complete revolution is 360 degrees. It's an equilateral triangle and 3 sides. So it has 3 sides. 3 goes into 3 once, 3 goes into 6 twice. So we see here, we have, if this is 120, this is 120, this is 120. We have three rotations, and it's back to the beginning. So, the rotational turns here are from A to C. That's 120 degrees. 120 and 120 is 240 degrees. That's the second one. So it's 120, 240 degrees. If I do it again, I get 360, and that doesn't count. So we have 2 rotational symmetries. And there you have it. It's just nice to look at it. Alright. So if you look at, we have 120 degrees rotation. We call that the alpha. And we have 3 sides, number of vertices. So we take n times alpha. We have 3 times 120. It'll equal 360. That's how we test it. Alright, let's look at some more. Determine the turn rotations of the following figures. Alright, so in this first one, if we put a pin right there and rotated it, this one would rotate. If I rotate it, then all these would be the same. So there's 1 rotation, 2 rotations, 3, 4, 5. So we have 1, 2, 3, 4, 5. So it's 360 divided by 5. Five goes into 36 7 times. 7 and 5 is 35, so it has 1 left over. 5 goes into 10. So from this one to this one is 72 degrees. From this one to this one, 72 plus 72, 144 degrees. From this one to this one, 144 plus 72 is 216. That's 216 degrees. And then we have another one. So it's 216 plus 72 is 288 degrees. And the last one goes back to the original. So we have 4 turn rotations. It's at 72, 144, 216, 288. Instead of writing all those, what we could have done is simply put n, or 72 degrees times n, where n at the most is 5. So we have 5 points. All right, next one. We have 4 points. This one to this one is 90 degrees. That's 90 degrees. So that makes it 180. Then to here makes it 270. From here to here, that puts it back at 360. So we have at 90, 180, and 270, which is 90n. And this one, now this one has 5 rotations. This one only has 4 rotations. It only has 1 rotation. It goes from here to there. So it's a 180 degree shift. Okay, now here's the center. If I rotate it out there, will they look the same? The inside looks, yes. Outside loop, outside loop. So it has 1 rotation at 180 degrees. There we have it. So, to find the symmetries, turn the object by rotating it until it matches the original shape. Measure the turn angle from the new location, which is what we did. We put a pin in this first one. We stopped right there. We rotated it from this line right here. We rotated it that until it's straight up and down again, and we measure this angle here, which is 72. Or we can do it my way. 360 divided by how many sides you have. how many vertices you have. Okay, determine the turn angle for the rotational symmetries of each of the figures below. Locate the approximate center where turns are done about each image. Alright, so the center is right here. Complete revolution is 360. I have 3, so it's 120 degree turn angle. $120, that's this one here. That's 240. And that's 360, not going to do so. These are the turn angles. Here's the center of the card. For rotate it, not 90, it would be 180 degrees. So it's 360. It only has 2 sides, so it's 180 degree turn angle. This one, the center is there. So I wanted to go that direction. So I rotate it until it's here. Now I measure this angle here. 1, 2, 3, 4, 5, 6. 360 divided by 6. 6 goes into 36 6 times. So each of these are 60 degrees. 60 degrees. 60 plus 60 is 120, 180, 240, 300, and then 360. So those are all the turn angles, the measures. You have to list all of them. All right. Point symmetry. Any figure has 180 degree turn symmetry about a turn center. So like for example, the letter H. If I find the turn center and rotate it 180 degrees, I'll get the same picture. What I do here is find where is the center. What you could do is just do diagonals, and where the lines cross, that's the absolute center. Bisect it again, bisect it, so we'll find the center of a circle. That's actually a center of a circle is much more difficult than it looks. Because, again, the work I just did there, one line was good, but then the next one was bad. How about this one? So I have a diagonal here, make 2 equal sides. I have a diagonal here, and I have a diagonal there. So where they intersect is the center. Since that's a line here, if I take both endpoints, it's if these are the same length. Where it intersects, that's the center line. Alright. And lastly, in this section, classification of polygons to their symmetries. Geometries can be classified according to the number of symmetries that they have. This is going to be interesting also, in that if you look at this one, the first picture is an isosceles triangle. Remember, isosceles has 2 sides that are the same. It has one symmetry. it's not across any other ones because it has to be the same on both sides. A rectangle has two symmetries. The diagonals won't work, but across the midpoints of the two opposite sides. Of a rhombus, we can't do it from the sides, because if we fold it, then it won't be the same picture. So we have to do it diagonally from across the vertices. We only have two. A square, all four sides are the same, and all four angles are the same. So if we did diagonals across the vertices, we have two there, and also across the midpoints of each side. So we have four here, two here, two here, and one there. All right, good luck everybody, and see you in the homeworks.